In the previous lesson, we covered one of two major categories that encryption ciphers fall into, symmetric key ciphers. In this next lesson, we'll cover the second class of ciphers, called asymmetric or public key ciphers. Remember why symmetric ciphers are referred to as symmetric? It's because the same key is used to encrypt as to decrypt. This is in contrast to asymmetric encryption systems because, as the name implies, different keys are used to encrypt and decrypt. So how exactly does that work? Well, let's imagine here that there are two people who would like to communicate securely. We'll call them Suzanne and Daryl. Since they're using asymmetric encryption in this example, the first thing they each must do is generate a private key. Then, using this private key, a public key is derived. The strength of the asymmetric encryption system comes from the computational difficulty of figuring out the corresponding private key given a public key. Once Suzanne and Daryl have generated private and public key pairs, they exchange public keys. You might have guessed from the names that the public key is public and can be shared with anyone, while the private key must be kept secret. Once Suzanne and Daryl have exchanged public keys, they're ready to begin exchanging secure messages. When Suzanne wants to send Daryl an encrypted message, she uses Daryl's public key to encrypt the message and then send the ciphertext. Daryl can then use his private key to decrypt the message and read it. Because of the relationship between private and public keys, only Daryl's private key can decrypt messages encrypted using Daryl's public key. The same is true of Suzanne's key pairs. So when Daryl is ready to reply to Suzanne's message, he'll use Suzanne's public key to encode his message, and Suzanne will use her private key to decrypt the message. Can you see why it's called asymmetric or public key cryptography? We just described encryption and decryption operations using an asymmetric crypto system, but there's one other very useful function the system can perform: public key signatures. Let's go back to our friends Suzanne and Daryl. Let's say Suzanne wants to send a message to Daryl, and she wants to make sure that Daryl knows the message came from her and no one else, and that the message was not modified or tampered with. She could do this by composing the message and combining it with her private key to generate a digital signature. She then sends this message along with the associated digital signature to Daryl. We're assuming Suzanne and Daryl have already exchanged public keys previously in this scenario. Daryl can now verify the message's origin and authenticity by combining the message, the digital signature, and Suzanne's public key. If the message was actually signed using Suzanne's private key and not someone else's, and the message wasn't modified at all, then the digital signature should validate. If the message was modified, even by one white space character, the validation will fail, and Daryl shouldn't trust the message. This is an important component of the asymmetric crypto system. Without message verification, anyone could use Daryl's public key and send him an encrypted message claiming to be from Suzanne. The three concepts that an asymmetric crypto system grants us are confidentiality, authenticity, and non-repudiation. Confidentiality is granted through the encryption-decryption mechanism, since our encrypted data is kept confidential and secret from unauthorized third parties. Authenticity is granted by the digital signature mechanism, as the message can be authenticated or verified that it wasn't tampered with. Non-repudiation means that the author of the message isn't able to dispute the origin of the message. In other words, this allows us to ensure that the message came from the person claiming to be the author. Can you see the benefit of using an asymmetric encryption algorithm versus a symmetric one? Asymmetric encryption allows secure communication over an untrusted channel, but with symmetric encryption, we need some way to securely communicate the shared secret or key with the other party. If that's the case, it seems like asymmetric encryption is better, right? Well, sort of. While asymmetric encryption works really well in untrusted environments, it's also computationally more expensive and complex. On the other hand, symmetric encryption algorithms are faster and more efficient at encrypting large amounts of data. In fact, what many secure communication schemes do is take advantage of the relative benefits of both encryption types by using both for different purposes. An asymmetric encryption algorithm is chosen as a key exchange mechanism or cipher. What this means is that the symmetric encryption key or shared secret is transmitted securely to the other party using asymmetric encryption to keep the shared secret secure in transit. Once the shared secret is received, data can be sent quickly and efficiently and securely using a symmetric encryption cipher. Clever, huh? One last topic to mention is somewhat related to asymmetric encryption, and that's MACs, or Message Authentication Codes. not to be confused with media access control or MAC addresses. A MAC is a bit of information that allows authentication of a received message, ensuring that the message came from the alleged sender and not a third party masquerading as them. It also ensures that the message wasn't modified in some way in order to provide data integrity. This sounds super similar to digital signatures using public key cryptography, doesn't it? While very similar, it differs slightly since the secret key that's used to generate the MAC is the same one that's used to verify it. In this sense, it's similar to symmetric encryption system, and the secret key must be agreed upon by all communicating parties beforehand or shared in some secure way. This describes one popular and secure type of MAC called HMAC, or a keyed hash message authentication code. HMAC uses a cryptographic hash function along with a secret key to generate a MAC. Any cryptographic hash functions can be used, like SHA-1 or MD5, and the strength or security of the MAC is dependent upon the underlying security of the cryptographic hash function used. The MAC is sent alongside the message that's being checked. The MAC is verified by the receiver by performing the same operation on the received message, then comparing the computed MAC with the one received with the message. If the MACs are the same, then the message is authenticated. There are also MACs based on symmetric encryption ciphers, either block or stream, like DES or AES, which are called CMACs, or cipher-based message authentication codes. The process is similar to HMAC, but instead of using a hashing function to produce a digest, a symmetric cipher with a shared key is used to encrypt the message, and the resulting output is used as the MAC. A specific and popular example of a CMAC, though slightly different, is CBCMAC, or Cipher Block Chaining Message Authentication Codes. CBCMAC is a mechanism for building MACs using block ciphers. This works by taking a message and encrypting it using a block cipher operating in CBC mode. CBC mode is an operating mode for block ciphers that incorporates the previously encrypted block ciphertext into the next block's plaintext. So, it builds a chain of encrypted blocks that require the full, unmodified chain to decrypt. This chain of interdependently encrypted blocks means that any modification to the plaintext will result in a different final output at the end of the chain, ensuring message integrity. In the next section, we'll check out some common examples of asymmetric encryption algorithms and systems. I'll see you there.